Now, going back to meaning here, we quote Steve Gould saying, human groups do vary strikingly in a few highly visible characteristics like skin color and hair form, and this may fool us into thinking that overall differences must be great. But we now know that our usual metaphor of superficiality, skin deep, is literally accurate. Other plausible scenarios might also have led to marked inequality. Homo sapiens is a young species, its division into races even more recent. This historical context has not supplied enough time for the evolution of substantial differences. But many species are millions of years old, and their geographic divisions are often marked and deep. Homo sapiens might have evolved along such a time scale and produced races of great age and large accumulated differences, but we didn't. Human equality is a contingent fact of history. Now that all sounds great, all right. But what all of us evolutionists, evolutionary biologists ought to appreciate is the one thing that could not possibly be a contingent fact of evolutionary history is equality. Because the evolutionary process runs on variation. No variation, no adaptation, extinction. So you have to have functionally significant variation in every species, in every population. So that the one thing you can't have is a bunch of actually equal individuals. That would make nonsense of the evolutionary process. All right? So Gould is wrong here before we start worrying about any data at all. And age, well, we're back to talking about dogs. All right, we'll only be doing these nasty things to dogs for really most of them a few hundred years, and we can reduce very large differences. And let's see what kind of functional variation we have in people. Let me first start with the morphology, and I'm going to do a little test here, okay? First, I'm going to give you only two people here I think know what the answer is to this question, and they'll keep their mouths shut. Let us say that I have a metric which assesses the degree of morphological variation in the face and the cranium. Classic anthropometric data. Okay? And I work this metric so that I factor out size. So in some sense, I'm trying to deal with shape. And my units of measurement are expressed the way Linda mentioned yesterday as standard deviation, and Carl did, as standard deviation units. Okay? And as an example, if I were to compare two Australian males, I might get a difference of about 0.8 of a standard deviation, okay, for about 25 to 30 face and skull measurements. If I compared, let's say, two females on the average, I might get 0.78. If I then compared male to female, the average might be 0.81. Now, the delta here, the delta male to female, is equal to 0.81 minus half the sum of the within-sex differences. In this case, just to one decimal point, 2.5.
By the delta, you mean the male-female difference?
No, by the delta, I mean the increase in distance in going from male-male or female-female to male-female. Okay. So in other words, I'm interested in the delta value here. This is what I'm going to ask you about. Now, this is a reasonably representative figure, around 2%. Okay,
let me see if I can. So what you're saying is that the average variation between two individuals of the same sex.
Yes.
If you then, sex differences add about 2.5% of that.
That's right. They add about 2.5%. Exactly. That's my delta, is that additional difference in going from the baseline comparison to the one one is interested in. Okay, now the question, everybody has to answer. Okay? If I were now to compare Australian male to Russian male, Okay. What would the increase be? I said that male-female, going from male-male comparisons to male-female comparisons in the same population is about 2% increase in difference. Now, if I go from male in one population to male in some other population, I said, say a European and an Australian, what will be the amount of difference?
This is an Australian Aboriginal.
Yeah, that's taken for granted. Yeah, not like Frank. Frank doesn't count. No, there's no Aboriginal in you, Frank. All right. Now I'm going to, okay. How many of you say about the same as the sex difference, about 2%? Frank? You all have to say something, all right? Nobody's testing you. Nobody's going to give you a grade. Okay. So the number of you who think that the race difference is about the same as the sex difference, couple of you, yes? Let's say twice the sex difference, so 4%.
I will say less.
Less than 2%. Less than 2. Okay. How many of you think less than 2? Okay. How many of you think twice 2? That is 4 or 5. Okay, well, what, 10? You think something. Šta znaš? Huh? Što znaš? Ništa. Huh? What about... Does it hurt you to raise your hand on an opinion?
They're in too much trouble now.
Maybe they haven't got the second part of the comparison. We're comparing sex difference with racial difference.
Right. We want to know how large is the race difference in comparison to the sex difference. I already told you the sex difference is about 2%. The major human racial groups. Australian European is about average.
They state that the racial differences will be more. So just raise your hand.
Okay, how much more? Okay. 10%? Is 10% too high for most of you?
Less than 5%.
What?
Less than 5%.
Less than 5. Anybody think more than 5? No. Okay. My answer, and if you want the specific math of how I got it, I'd be happy to tell you. Okay, I was going to do this up here, take the rest of the period. The answer for between Australians and Europeans is 25%. Ne može to biti, yeah? Is that right, Marina? Ne može. Okay, I'm not. We can discuss how I did this, or if you have any specific questions. But that is. Let's put this in context, and then we'll go 30 seconds, and then we'll go have our break. Now, so I was really interested here in trying to place the degree of racial morphological variation in our species as compared to non-humans. So here are some between-sex differences for 3 human populations. Santa Cruz, by the way, is an island off the coast of California. Now, here are 2 comparisons within chimpanzee species for male-female differences. And as we would expect, the pygmy chimpanzee sex difference is about halfway between humans and the larger chimpanzees, and for the larger chimpanzee, the sex difference is about 10%. Now, if we're talking about between populations, here are some African comparisons. For the first three are African comparisons. Then we have South Australia and Norse at about 26%. And then the largest differences that one finds in human beings are between Africans on the one hand and Mongolians or American Indians on the other. Those are the last three in this series. And then I add here some interspecific ape comparisons. So if I compare the pygmy chimpanzee to two subspecies of the common chimpanzee, I have about a 9% difference and about a 15% difference. And if I compare the two gorilla groups, that is the eastern and the western gorillas, I get a difference of about 21%. So that the human morphological differences can be as large or substantially larger than any difference that we see within or between ape species. There is a lot of racial variation in people, and it isn't just skin deep. I leave you with that thought. I'll see you in 10-15 minutes. Morphological distance measurements. Those are all involving size-corrected measurements in the face and in the cranium. And as far as the math is concerned, I will write out, the math is very simple, all right? I will write out how I got the numbers. And if somebody can copy them, you can have copies then while I'm still here, rather than having to do it on the internet. And as Frank says, try to be slower and clarify terms. I'm trying, okay? And the other thing is that there has to be a two-way matter here. If you don't understand something I say, wave your hand and say "Stayato" or whatever, okay? Now, I want to mention just one more morphological distance type number, and this has to do again with antiquity of racial lineages, and specifically has to do with European area fossils that are between about 15 and 30,000 years of age. One of them being, I'm not sure whether Kostenki is Russia or Ukraine, but anyway, one of the specimens is south of here, but in this general area. And what I did there was to measure the average distance from those 17 fossils to a series of 5 human reference populations. Here. So that what we see there is that the average distance from the 17 to each of the 5 human reference populations, Anyang is a 3,000-year-old Bronze Age site near near Peking. Santa Cruz, I've already told you. Tolai are a bunch of people from New Britain. Zulu, you know. Norse, you know. And what you see is that those fossils are about equidistant from all of those recent modern human populations, which is saying that, that racial lineages, here we're talking about European ancestry, that even though these fossils are European area fossils and are not all that ancient, nonetheless they do not show any particular affinity with existing European populations. So the actual characteristics which characterize recent and existing races must be very recent indeed in development. Okay? Now, morphological or behavioral differences. I think that before I give you the numbers, we're going to do another test. Imagine this experiment. Imagine that I take a randomly chosen sample. That is, I pick people blindfolded from, let's say, a group of males aged somewhere around 30. Somewhere, let's say, between 25 and 35. And this is a random sample of males. I now take them and I train them for running. And I train them until their performance level starts leveling off, in other words, where they seem to be stopping a significant improvement. I now have them run a marathon. A marathon is 42 kilometers. And the best humans can do a marathon in 2 hours and 10 minutes, about. What would be the average for my randomly chosen and trained sample? Okay, we're going to vote. Let's see if anybody, let's say less than 3 hours. How many of you think that the average for this group would be less than 3 hours? Okay. The best, about 2 hours and 10 minutes. Okay, less than 4, let's say 4 hours. Okay. 5 hours. More than 5 hours. Very good. You are the first group that has given me what seems to be the correct answer, working this out from mean performances and the spread in performance in large competitions. That in fact, it looks as though it would take the average individual somewhere on the order of 4.5 to 5 hours. That is at least twice as long as it takes the best people to finish. And of course, for many of us, it would be a lot more than that because we couldn't run that far, literally. And you can walk, if you're in anywhere decent shape, you can walk 26 miles in maybe 9 hours or so, okay? And that probably would be kind of the upper limit. But so that what we're looking here is in an area of the body which has clearly been under very intense selection for several million years. We nonetheless have an enormous amount of variability in performance still present. Okay. 2 hours, in other words, if you were running a race up and back, say 20 kilometers up and 20 kilometers back, you'd have some people finished before most of the people gotten around the turn. That, to me, is huge variation. And at the populational level, now here we were talking about, I wasn't choosing population, but at the populational level, let's talk about the largest differences we know about as far as group differences in athletic performance are concerned, in simple athletics, okay? I'm not talking about team sports here. Now, there was starting with the races in 1997, every year there are cross-country championships. This is 12 kilometers up and down hills. And this, where I noticed it, was in Turin. There were 275 runners from 60 countries. And the Kenyans took their, as I say, 12th straight team title. It's now, I think, 16 or 15 or 16 team titles. And they placed 1, 3, 4, 6, 7, 17, 19, 24, 28, and 47. So you could only have 10 entrants. The worst Kenyan placed 47th. Now, the winning time was 35 minutes and 11 seconds. The Kenyans averaged 36 minutes and 4 seconds. So the 12 Kenyans averaged less than a minute worse than the best individual. So the average Kenyan would have finished 12th overall. And as I point out here, as many of us are aware, it's not even that simple, because most of the runners over time from, quote, Kenya, unquote, have actually been from one small mountainous area of Kenya. There may be 3 million people in that area, maybe less. And over those, well, now it's 14 or 15 years of Kenyan domination, these runners would have won the team title 8 times just by themselves, leaving the other Kenyans out of it. And they have taken 18 out of the 36 medals. In other words, first, second, and third place, 3 medals in each year. So over 12 years, we're talking 36 medals. This group of Kenyans took 18. So a group of 3 million people took 18 medals, and the rest of the world, that is 5 billion people, took the other 18. And actually that's a number that's been reiterated in a number of races. For example, the Boston Marathon just a couple months ago, where there were 8 Kenyans in the race. They didn't win for the first time in 11 years, but the worst Kenyan took 17th place. So of the first 17 places, 8 were Kenyans, all right? 8 for Kenya, 9 for the rest of the world. For the last dozen years or so, the typical result. Now, what does this say about the average difference between this Kenyan group and the rest of the world? What we're interested here is some sense of population or racial comparisons. Now, what we have is a ratio of success, okay, of, well, 3 million of these people, 5 billion people in the rest of the world. That's a ratio of 1 to 1,700 in relative performance, okay? You're 1,700 times more likely to be a winner if you come from this group in Kenya than if you come from anywhere else in the world. Or, I'm sorry, any other specific place in the world. Now, we can then look at, let's say, the performance of the best as a something like a 1 in 20 million or a 1 in 30 million performance. That's what I have here. And that means that the best individual is somewhere 5 to 5.3 or so standard deviations better than the average. The Kenyans, okay, are 1,700 times better off on this scale than others. 1,700 times 0.032. In other words, instead of their probability to be 0.032, they're 1,700 times 0.032, and that's about 50. So that takes us to somewhere around 3.8 standard deviations. In other words, the best Kenyan is about 3.8 standard deviations above his country's or his nation's mean, population's mean. The best in the world as a whole is about 5.4 standard deviations above the mean. So the difference between the world as a whole and this Kenyan group is about 1.5 standard deviations. That is a whopping intergroup difference. And as Steve Saylor sort of quipped, noted when I first put this out on the web, we could say that this group of Kenyans had an RQ, that is a racing or running quotient compared to IQ of about 122. Okay. So this, I think, gives lie to the idea that functional differences among modern human populations are minimal. And to try to push this even a little further, this level of difference implies that the best 10 women from this group, if there weren't any cultural barriers to having the women running, okay, and those are breaking down, that the best 10 women from this group would in fact beat most teams made up of the best men, 10 best men from comparably sized populations. For example, in New Zealand, we have about 3 million people. That means that if you took the best 10 male New Zealand marathon runners, the Kalenjin women could beat them. That's what these numbers imply. Okay? Now, one of the problems that one runs into here is that people argue, on very good grounds, understand, that these sorts of results, in a sense, shouldn't be. Or, more fairly, that these sorts of results do not indicate genetic differences. Because if they did, let's imagine that we were selecting for characteristics like running ability or brain size or whatever, okay? That if you had respectable levels of selection occurring, then in fact you ought to take out the variation from the population and therefore reduce the heritability of the remaining variation. This is a standard argument in evolutionary biology. You'll find it in genetics textbooks, evolutionary biology textbooks, that selection narrows variation. Okay. The only problem with this argument is that it isn't true. Okay. And I'll give you an example. There's been an experiment, and this is not an atypical example, right? This is taken from a book of such examples. There's been an experiment running at the University of Illinois in Champaign, Illinois, in the United States, for, when this paper was written in 1989, about 90 years. The experiment had been started from, I believe, 12 ears of corn, somewhere around 1890, somewhere around 1890, and they then selected the corn for high oil content and for low oil content. And they have kept that experiment going now for almost 100, well, it is now about 100 years, although I don't have the most recent data. So what we see here, there you go. No. We see here that the oil content percentage at the beginning was somewhere around 4.5%. And starting, it seems to have gone up pretty steadily, pretty good straight line relationship there, with no evidence of turning over, up until so that the content now is around 21% in the high oil strain, and down to close to 0 in the low oil. Well, obviously there's a bottom here. You can't get less than 0. And there presumably is a top too, because there's a limit to what percentage of oil you can have inside the kernel. But what is indicated here is that very intense selection over a 100 generations of corn, in fact, has not reduced the underlying genetic variability. Now one can ask, how can that be? I mean, we're doing genetic selection here for sure. There's no doubt that these features are genetically controlled. We're selecting for different yields, either high yield or low yield. And we don't seem to be using up the variability because the rate of change isn't changing. That is, the fund of available variability seems to be remaining pretty constant. So, what's going on? Well, at least what I think must be going on, is that that any characteristic of this type, like oil yield or running ability or brain size or any of the other things that we're interested in, which are innumerable, that those are polygenic characters, that there are many, many loci involved in the final product. And yes, we may be selecting at one locus in this experiment and reducing variability at that locus, but there's a whole bunch of other loci around to retain a great deal of variability. And I think that this is what's going on, and this is the answer to people who argue that, in fact, if things are particularly important to the species. If there's high selection involved, therefore, the variability in the characteristics that the heritability of the variability in the characteristics must be low. So people argue, for example, that the heritability of intelligence can't be very high because it's been such a very important feature in human evolution. But what I want to reiterate is that the underlying logic is faulty. And so, as well, there is a lack of positive evidence demonstrating that, in fact, fairly intense selection will reduce overall genetic variability with respect to the feature that one is talking about. Okay.
Can you repeat that?
All right. We have a feature. We were talking about running ability or brain size, all right? We know that both of those have been under intense selection in our species. Bipedalism is a very tricky adaptation to manage mechanically, okay? Brain size is very expensive, as was reiterated in the birth scenes a couple days ago. The argument is then made that characteristics like that are particularly important, will have been under intense selection, and therefore the genetic variability or the genetics underlying the phenotypic variability would have been reduced. That is, we would have selected out the variation and left everybody more or less the same ability with respect, or the same characteristics with respect to brain size or running ability or performance and intelligence tests or this or that or the other thing. But if we look at people, not just corn ears, the fact is that there is an enormous amount of residual variability. Variability in brain size has not gone down over time. As far as
There's no finite number of loci here?
there's presumably a finite number of loci, but the number is large enough so selecting at 1 or 2 or 3 or 4 of them is not going to change things very much as far as the whole is concerned. That the total amount of variability, genetic variability present, is not significantly changed.
Is it possible that over sufficiently large span of time, all the genes involved would be selected for, despite their great number?
Alex, I'm not sure what you mean by all of them could be selected for.
The number is finite, finally you'll select for all the else.
That eventually you'll select for all of them, and that then you will have reduced, variability. Well, you have mutations coming in. And so you've always got those coming in. And clearly, if you start reducing variability, you start being at a real selective disadvantage to populations which retain variability. And in fact, you know, no, I'll let that go at that. But this is a point I haven't heard made very many times before or elsewhere. And in fact, this example came up in 1988 in a seminar I was giving in Berkeley. And I had a couple of population genetics students in that seminar, and this question about how do we retain, for example, brain size variability in the face of what must be very intense selection and counter-selection on the characteristics, how do we retain the variability? What about this business? What is the evidence that selection truncates variability? Okay, so I remember one of them went out to the library and researched the genetics library, and first found minimal documentation of the idea that selection reduces variability. And then she cottoned onto a paper by Richard Lewontin and one of his students, in Drosophila, of course, and I don't remember what was being selected for or against, but in fact they were addressing precisely this question. And what they found was that no, the underlying genetic, the additive genetic variability was not reduced in their selection process.
I'm very slow on this, but if you only select for 5%, how does that have such a phenotypic effect?
I'm sorry, now I've lost.
Selecting on 5% of there's something here that brought in 5% of loci are being selected. You only,
Oh, I don't think 5%. I mean, presumably some minuscule fraction of a hundredth of a percent.
worse, but you still get those phenotypic changes. That means they're very causally affected.
There are a lot of loci available to affect the phenotypic characteristics. I mean, to affect the variability in any given phenotypic characteristic. That's the point. That's the message. Okay.
But you reduce the phenotypic variability.
Not particularly. No. No. I mean, this has moved. At least the high yield, the high oil strain has moved something like 5 standard deviations during the experiment. But the variability at any given point in time has not really changed. The variability is still there.
So you shift the mean value, but not the variability.
Exactly. You shift the mean, but not the variability. And this is what you look. If you look at characteristics in humans over the fossil record time, you don't find that you would think were the more intensely selected features are more variable or less variable. I mean, if we talk about brain size, which I think is the diciest character here, because I mean that's got to be under very intense selection and some sort of balancing selection. If you look at brain size variability, it's not anything out of the ordinary. The standard deviation of brain size is about 10%, something like that, about 125 to 150 cubic centimeters. Now we don't have a decent fossil record to a statistically significant sample, but that 10% is nothing different from chimpanzees or gorillas. That's a perfectly reasonable volume, character, range of variation. But that, yeah, and as Linda said, inbreeding. So people inbreed strains of rats for umpteen generations, and so those are highly inbred and highly homozygous at many loci. Yes, it can be done, but it's not something that I think happens very often in the, quote, natural world, unquote. And I don't think it can be used as an explanation, well, the way it has been used in recent years, in particular, for example, arguing that intellectual performance can't be highly heritable because if it were, the variation would have been selected out. And the fact is that intellectual performance is highly variable, and there's no evidence that it's been reduced over time. Let me mention one sort of historical type, by my standards, experiment here. When Allan Wilson and I were doing our work early on in the mid-60s, we found that rates of change of the same protein along different lineages were very stable. Okay, and so in other words, rat, even though the generation times involved were enormously different, the albumin or transferrin, that's 2 serum proteins of rats, were not changing any more rapidly than the corresponding serum proteins in people. And neither Allan nor I were population geneticists, and we had a very difficult time in understanding how this could be true. I mean, how was it possible that a very short generation length organism would be changing its genetic characteristics at the same rate as a very long generation organism? And we really didn't get very far with this thinking until Jack King, who was a population geneticist, gave a seminar at the lab. And he wrote down, I'll see now, it's worthwhile doing this. What is, now you're not supposed to read that, okay. He said, what is the rate of introduction of new mutations into the population? Well, that's just the mutation rate, mu. how many new mutations will you get in a new, going into the population? Well, it's the mutation rate, which is given at the for individuals, times the number of individuals in the population, which is 2n. So 2n mu is the number of new mutations in a given population in a generation. Now, what is the probability that that mutation that will survive to become the dominant one, that is the high frequency one, at some time millions of years in the future? Well, there's one of them, okay, and what we're imagining here is that it will increase in frequency to something like 100% X years into the future. What is the probability that this one will make it? Well, it's simply 1 over 2n. That cancels out. And what comes out of this is the notion that the rate of change, that the likelihood of a mutation surviving is equal to its rate of incidence. Population size factors totally out of the equation. Okay? And when Jack King wrote this on the board, I was quoted in the Science magazine issue a couple months ago as having had an epiphany when I faced up to the Y chromosome and mitochondrial data that I was talking about earlier. Well, this was my earlier epiphany, because we were having this thing, we couldn't understand what was going on, and Jack just wrote this one equation up there, that equation. Oh, that's how it works. That's why molecular clocks exist, and so forth and so on. And the only remaining step, okay, was this business of, well, shouldn't short generation length animals be able to turn their genomes over more rapidly, have more mutations being fed through per unit time? Well, in theory, yes. In practice, as I said, no. Why? Well, now we get back to this business of variation. If, in fact, some organisms had mutation rates that were higher than other organisms, let's say that rats really had higher mutation rates than people did, measured per generation, okay? Or per year. Well, then, in fact, rats would have more variability with which to evolve, on which natural selection could act. In which case, what you ought to have is a tendency to shorter and shorter generation lengths. Again, something that has clearly not happened in the evolutionary record. So what comes out of this, apparently, is that everybody is running as fast as they can. Now, are there... No?
I just want to say immortality is in great risk.
Well, immortality is something that the evolutionary process can't allow, because immortal forms couldn't evolve, and so they'll be wiped out by mortal forms. It's tough on us oldsters, but that's the way life goes, okay?